Welcome. This is a recorded session of the Post-Quantum Cryptography Conference of the PKI Consortium, which took place in Kuala Lumpur, Malaysia. This conference is made possible through the support of the PKI Consortium Post-Quantum Cryptography Working Group and our sponsors SSL.com, Entrust, Keyfactor, HID, and Crypto4A. And with exceptional organizational support from SSL.com, Keyfactor, Logius, POS Digicert, Baker Tilly, MSC Trustgate, and Digitoris. Join the discussion. Join the PKI Consortium. Go to pkic.org/join.
Well, we're probably close enough to kicking off the second session in this afternoon block. So right now I'd like to welcome to the stage Murali Dhuran, Palanisamy. Pretty close. Close as an Australian's going to get. Australian and India playing cricket at the moment, so it's probably about as close as it's going to get. Murali is co-founder and Chief Solutions Officer at AppUX. His bio on the website says he's been doing this for 20 years, but earlier today he claimed 25, so we'll take the extra time. And we'll leave it over to you, Murali. Thanks.
All right, thank you. Hello, everyone. Today we'll look at post-quantum in a pretty little bit larger lens, to say, just instead of focusing only on the crypto, looking at the WebPKI as a whole, and how we can use the quantum challenge as an opportunity to redefine, or rather update or upgrade the architecture, the WebPKI architecture. So first, let's start with what is WebPKI. So WebPKI primarily focuses on the confidentiality and integrity and authenticity of communication between a web browser and the web server or a CDN provider and whatnot. So what it entails, obviously the certificate authority, the certificates and keys, and then the CRLs and the CT logs, the whole slew of things which is needed for the web browsers to securely communicate and authenticate web servers, which is where majority of our TLS traffic or majority of the websites or the internet or the use cases is going to be, right? Now, in this, one thing that we observed, right? So we do a scan of the internet, and we look at how things are, where things lie in terms of crypto, and how things move and stuff like that. So we do this every year, and this year we did it a little early, and we also ran it again at the actual time as well. So we focus on the Fortune thousands, again, to make it easy to align. So we do have the data, which is for the larger systems as well. But on the Fortune thousands, when we looked at last year, the TLS 1.3 adoption was like 75%. So the year before it was like in 60s, right? But this year, in 8 months, that increased to almost 90%. And today it's almost like 91%, or I guess, right? And of these, majority, 74% or 75% close to was RSA. And I have this DNSSEC reference. It's more to show you how things move in the internet. DNSSEC adoption was 4% last year, and same the year before. And it stays the same this year as well, right? But then when you look at the TLS 1.3 adoption, it has reached almost 90%. It's actually 400, of the 1,000 Fortune thousands that we see, right? So there's a pretty significant increase in the number of Fortune thousands upgrading their stack, right? And this has happened in the last 8 years. The other important data point I want to bring to your attention is that last year around this time is when NIST sort of agreed or standardized on the post-quantum algorithms and key exchange. So today, 41% of the Fortune thousands today use post-quantum hybrid key exchange today. Right? In 8 months, getting to this level is unimaginable, right? The interesting factor, if you peel the onion, is I see there is a sort of a divide between the big tech and the enterprises. Now, there is another interesting data point is that the TLS 1.3 support, I mean, this is the best supported algorithm for Fortune thousands, right? Now, when you look at who is still supporting TLS 1.3 as their best algorithms, interestingly, it is some of the financial services. Again, because of their visibility and a whole bunch of other requirements and all that. But that said, the reason I bring this to your attention is that there is a focused area in WebPKI, and there is a shift happening in the enterprise. Now, when we look at implementation of PQC, when we focus primarily on WebPKI, there are clearly some of the important challenges. One is, we all know that the key sizes are going to increase, or the signature sizes are going to increase, which means the TLS handshakes, the time to first byte is going to increase, right? And there is going to be higher memory cost because of the signatures that are there. And then, especially when you're looking at hybrid and legacy and post-quantum key exchanges, that is going to add an additional level of memory and then volume. And hybrid key exchange complexity, that also, even though 41% have implemented it, there is an underlying cost to it, right? So this is the reality. And when it all, what all this boils down into the website performance, right? Now, when we look at some of the applications, like trading applications and low latency requirements, right? Like when you in some of the trading platforms, you have real-time codes, which means that when you turn on real-time codes, that data, has to be transmitted to the browser in real time. So all of those things have an impact when you start enabling the post-quantum algorithms. Again, Cloudflare has published some of the metrics. Again, I think everybody has spoken about this. It's pretty clear that the total bytes that gets transmitted is way higher than what we would want in terms of a post-quantum TLS deployment or TLS handshake, right? So that said, so now let's look at HTTP, right? How it has evolved, and a little bit into the performance metrics into HTTP, since we are looking at website performance and web performance and whatnot. So HTTP 1.1. Oh. What's happening? Doesn't want to move forward. All right. So HTTP 1.1. This requires multiple TCP connections. So when you open a browser, type google.com, typically 4 to 6 TCP connections get established. There are, each one has to go through the three-way handshake and establish a TCP pipe, right? And with 1.1, one of the key challenges was that it's one request per connection. So which means you send a request, you wait for the response, and then you send another request. So which means it's a little bit sequential, and the page load time, the time to last byte, depends on how long it takes to get the data over to the browser. Now, HTTP 2 sort of addressed some of these challenges, where you could have multiplexing, Instead of sending a request, waiting for the response, you can send multiple requests and wait for the response. Now, even there, basically because of the TCP blocking, it has to, you have to wait for the first response before you can get the second response. So there's a pipe, and whatever comes through the pipe is what it is. Yes, you can open multiple pipes, but still there is a problem, right? Especially with lower 5G, 4G, or mobile applications and whatnot. It does improve on what was up there, but then it still has its own challenges with here it is. This gives you a pretty better view of what it is. So one of the important challenges is the head of the line blocking, which is if an object takes a longer to download, then everything else is waiting behind them, right? So HTTP 2 solved it. It increased a little bit of benefits and whatnot. But then there is still, from a performance perspective, there is still a problem. Now, HTTP 2 also brought in TCP stream. So instead of getting text-based updates, you get a stream. So it's a binary stream that you can download. So it's a little bit faster in that aspect. Also, header compression and other aspects came in. So this sort of helped us to have a lot better performance per se. But still, with our PQC adoption, the benefits of HTTP 2, we're going to lose that with the time to first byte delay in the TCP handshake. Now, Google has been proposing QUIC and has been using QUIC for a while. Now, what I call this is the post-pandemic babies. Right? So all these protocols are standardized after the pandemic, like after 2020s. So now that this has been standardized, what we see is the big tech are using them today, right? Like Facebook, Google, Netflix, even CNN, a whole bunch of these big tech companies which are primarily focusing on their web performance and web delivery. They use QUIC as their primary mode of delivery, right? Now, what is QUIC? Let's look at it a little bit. QUIC UDP interconnect. That's what it was supposed to be, but it's not an acronym anymore. QUIC is the name of the protocol. So even though underlying it uses UDP, it's sort of because it uses the UDP with the OS, all the protocol handling is done by the application. So in other words, it sort of removes all the complexities of a legacy TCP, which has its own overheads with flow control and window sizing and all that. Anybody who's done troubleshooting with TCP latency or troubleshooting the network issues, right, would know the challenges in looking at the window sizes and retransmission rates and all of those, right? So what QUIC does is it sort of removes all that overhead from TCP and uses UDP as the underlying protocol, and it enhances that with a one round-trip time handshake, especially from a TLS perspective. So when we look at TCP with TLS, when we compare TCP TLS with a QUIC, in TCP TLS, first you need to establish TCP, which is one round-trip time, the SYN/SYN/ACK, right? And then you have the client hello, and then you establish the TLS session, and then you start the data request, right? Whether it is HTTP 1.1 or 2 or whatever, right? There is 2 round trips before you can request data. So the time to first byte is after the 2 handshakes. And especially in scenarios where there is mobile or 4G latency in intensive networks, that sort of adds quite a bit of overhead. On top of it, adding our PQC data, which is the signature sizes, which are way bigger, it sort of slows it down quite a bit. Now, when we look at QUIC, it is, I start with a client hello, it's UDP, right? There is no connection. And the benefit is that there is zero round trip time option. If the client has already established a connection before, it can start with a zero round trip time by sending the request. Now, when you look at the browsers, most of the time, if you have used CNN, your bank website and whatnot, you are not going to go there for the first time ever, unless you clear the cache or got a new laptop, whatever, right? But then when you're using that often, it is almost zero round trip time, which means that you can cut down from almost 3 round trips in a TCP TLS to a 0 round trip in a modern QUIC deployment with PQC. So this way, one of the challenges that we have, which is the overhead of the crypto, could be balanced in a way with the protocol upgrade. This is where we look at this in a holistic picture as a whole, right? So if you compare all the HTTP2 with TLS, TCP TLS, and looking at the QUIC, if you look at it in the OSI layer, there is TCP and then there is the session layer, which is the encryption layer, and then comes the HTTP layer. In QUIC, it uses UDP primarily for the transport, and then the QUIC does all the flow control, crypto handshake. It's still under the hood uses TCP, but then all that is handled in the application layer, right? So what this does is it basically adds a little bit of overhead on the application, which is there's a CPU overhead and whatnot. But that said, because we have the ability to absorb it on the application layer of the web servers and the CDN providers and whatnot, so this has been a lot more useful for the big tech to implement. Now, one of the key challenges I see, or there is a divergence I see, is that of late, right, there is sort of a big wedge or a K-shaped movement between how big tech uses technology and then how enterprises use technology, right? So if you look at how CDN providers, even in the quantum, post-quantum world, right, how CDN providers support post-quantum hybrid key exchange and whatnot versus enterprises do. Very few enterprises are able to accelerate and get upgrade and get the services out as a big tech does. So this is an example where the big tech has started implementing QUIC and then is already out there and then able to demonstrate the benefits and performance benefits of that, while traditionally the enterprises still use some of the TCP TLS and legacy as what we call legacy, the pre-pandemic world as the legacy world still today, right? And this is where we have an opportunity to look at it holistically, because with post-quantum, it's not just upgrading our TLS stack or even what we use from PKI perspective and whatnot. Because it involves application layer changes, because it involves network level focus, and also crypto layer changes, looking at this holistically makes a lot more sense. Now let's look at the performance numbers. Again, we have our performance numbers. This is from University of Colorado. So I captured their data because we haven't published ours publicly yet. So these are public numbers which was already there. I think there was another version of the slide where I put the source. So, but anyway, it's fine. So here, if you look at this is comparing an RSA 3072 size key to a DSA MLDSA with all the FIPS, NIST standards, level 2, 3, and 5. So if you look at the performance numbers, right, they are sort of pretty well aligned on the network drop rate and on the response rate as well, right? And the reason is because of the QUIC sort of absorbs some of the delays or some of the overheads that PQC was adding. So if you look at the handshake duration between TCP and QUIC, there is a pretty clear difference. There is a pretty stark difference in terms of the time taken for the handshake because of that overhead, right? So RSA with QUIC, you see a significant difference. But when we look at the dilithium MLDSA keys, right? So even in that, there is still, it's not as significant as RSA, but still there is a significant improvement in terms of performance, right? Now to conclude, everybody knows PQC adds an overhead, right? It's given. This is what it is. Maybe we can mitigate it with having a PQC root and then a short-lived leaf. Until we have time, we can punt it out and whatnot. But still, this is a reality. Now, when we look at WebPKI, especially website performance and whatnot, we need to figure out how to mitigate the overhead. And QUIC offers a pretty good alternative to enable or reduce some of the overheads. Now, one additional benefit of QUIC is that just like how TLS 1.3 and 1.2 were set up, QUIC, the way browsers work is, it is an option, right? If the browser supports it, the network supports it, you use QUIC or you fall back to HTTP2 or TCP TLS, and then it'll still work. It'll be a little bit slow, but it's still okay. It's not going to break anything, right? And then from an enterprise implication perspective, you are upgrading to a modern stack, both from a protocol perspective, both from a website performance perspective, and also post-quantum crypto perspective. So you're making it secure, you're making it faster, and you're moving closer towards what big tech is doing. Now, it's easily said than done. There is a lot of middle boxes that needs to support QUIC as well, like the firewalls, Palo Alto firewall, Checkpoint, and whatnot. And the other easier option is to use CDNs like Cloudflare or Akamai, which would front-end it. It will talk QUIC to the browsers, while behind the scenes it can use TCP TLS or whatnot, right? If your web servers are not enabled or updated. So there are different ways to mitigate this, and that also solves your crypto problem of our hybrid key exchange problem, where those front gatekeepers can handle the hybrid key exchange and also post-quantum certificates, while the backend can still stay safe and where it is. So path forward, look at how it can be tested, look at interoperability. I mean, it is working, it is out there in the internet. So if you're using Google, you are using QUIC. Right? If you're using CNN, you're using QUIC. So this is the best way to look at the latest standards and then upgrading the enterprise to the best standards what is up there, right? Especially when we are looking at a strategy for planning post-quantum migration. This would help architect a holistic approach than I don't want to call it myopic approach, but a focused crypto approach. And that sort of gets a better visibility from board and architecture teams and whatnot.
Thanks, Murali. So do we have any questions for Murali in the room? There's one up here. Let's grab that. This is the Price is Right. You have to come down.
Thanks for a wonderful talk. I understand UDP being used for media and streaming, but are you also recommending, or is QUIC being also recommended for other transactions like banking and other cases as well?
Well, here we are focusing primarily on the WebPKI, anything that is involving a browser and a web server. So in your question, if you're talking about transactions using a web browser, yes, we could, right? But it is not restricted to the web browser, right? So QUIC, as long as you use a QUIC client, I use an OpenSSL client to establish a quick connection. So you could use, as long as the client is able to use QUIC, you could use that for an optimal response, because it sort of removes some of the overheads of TCP, right? And see, TCP is not going to change. It is what it is, right? But then UDP is one connection less. From a reliability perspective, retransmittation, all those things is what application level we have to take care. But if you have a reliable network, right, and if you want to use it for other use cases, it would be a lot faster, in my opinion, than anything else.
Right. Two more follow-up questions. Are you recommending, well, in QUIC, it was not clear whether you're recommending to upgrade a DTLS with chems, with PQC chems, or QUIC already takes care of those things?
No, see, my argument is that we have to look at this holistically, right? Now, what key you use, right? That is based on the performance test that you do, and the requirements that would come up and all that, right?